Hi everyone, welcome back to class. My name is RJ, and this is Design for Dynamic Wearables, a course where we take a look at computational design techniques through the lens of body architecture, fashion, and accessory design. So today I wanted to make a quick note on a technique I often use after I design something, but before I go to 3D print it. So it's really important when you go to manufacturing that the scale of the object you're making is one-to-one with real life. A lot of the time in 3D, we might be abstracted from scale, but ensuring that we have the correct scale on our export is crucial. So a lot of the time when I make a piece for the body, such as this earring here, I want to make sure that the size of the earring is going to fit with the size of an average person. It doesn't have to be exact, as I'm just making some prototypes here, but it's good to get the first print out at a good scale so you can have it in your hand, feel it, measure it, and make the necessary adjustments. But sometimes if you have something like a ring and you know the band size, it's a lot easier. But a nice general way to find scale in 3D when you're going to real life is to pick two landmarks on an object, measure those in real life, measure those in 3D, and then make sure the distance between those landmarks in 3D is the same as it is in real life. And you can do that with something like calipers in real life, and you can find exact measurements of objects and measure those again in 3D. Or we can make the measurements a lot more general. And something I like to do, especially with the body, and sometimes it can be hard to find good landmarks on the body to make measurements between. There's no hard edges. There's rarely any good spots that you can find on the body that you can line up with something in 3D. But something very general that I like to use is height. And I like to use the height of a person just because it's going to be one of the largest measurements and one of the measurements that we have the most leeway on if we get it slightly wrong. So why do I say this? For example, if you were to measure the length of your finger and get that measurement off by a couple millimeters, say for a ring or something, when we go to scale up our design, the difference of a couple millimeters could throw off our scale wildly. Now, if we measure the height of the body and say we get that measurement off by a couple millimeters, we're not in as bad of a spot. Whereas if we measured something really small and got that off by the same amount, we'd be in much more trouble. So I like to use the height of the body, and there's a very easy way to measure this in Grasshopper, and a way that I like to use a lot. So let's build that out here very quickly. Basically, what we're going to do is just find the height of the body. And it's really easy in real life to do it because you can stand next to a wall, put a measuring tape up, get that height. In 3D though, it's a lot more difficult to model all that to get that height. You know, we could put a line from somewhere on the bottom to somewhere on the top and say take that measurement, but as we can see, this line isn't great. It's going to be very wrong. It's not even going to the top of the head or the bottom of the foot, and it's not straight at all. So I like to do everything in Grasshopper, and there's a much easier way to find the top and bottom measurement with just a few components. So we'll start by taking the mesh and internalizing that into Grasshopper. We can then create a bounding box around this mesh. Make sure there's just one box for the mesh. If there's multiple, we can go union box. Same result here though. Now, with this box, we can find the distance between this perfectly flat top face and this perfectly flat bottom face. And how do we do that? Well, we can start by deconstructing this B-rep. What this is going to do is it's going to give us all the faces here in a nice list. And with these faces, we can take the area measurement of that face. And what this is going to do is it's going to give us the centroid of that face. We can see that represented by these green dots here. We have one on every single face. And you'll notice now we have 1 point on the top and 1 point on the bottom. So if only we could find the distance between these 2 points, we can measure this height very accurately. So how do we do that? Well, first, let's deconstruct these points. And if we look at the Z values here, this is giving us a value of every single Z position of every point. We can see on the list here, we have all the middle points around the circumference of the box, around 80 or so. And then we clearly have the bottom point at -11 and that top point at 172. So now if we can only find the delta between the top and bottom points, that would give us the height. How do we do that? Well, let's sort these points. This sort component has keys to sort. So if we had, say, a set of 2, 3, 1, it's going to sort that into 1, 2, 3. Very simply, that's all it does. So if we give it this list of these values, it'll sort these from smallest to highest, -11 up to 172, which is great. So if we look at the other input here, the values, this is going to take another list and sort it in the same way. So we can't really sort these points, but we can sort the numbers. So we sort the numbers, and then we take the points along for the ride, and this is going to rearrange the list in the same way as it's doing the numbers. So now the lowest point is going to be the first one, and the highest point is going to be the bottom point. So now we have it sorted and we can actually get a point list to look at these points. Let's make this size much bigger so we can visually see them. Okay, so now we have 0, 1, 2, 3, 4, and 5. So the first and last point are now easy to grab. So we can grab them with a list item. So we can take those points into the list. And right now, by default, it's grabbing the first item at index 0, which is going to be this bottom point here. But we want the bottom and top. So easy way to do that is to zoom into this list item here and just press this plus button above I, which is going to give us negative I. So this is going to give us the last item in the list and the first item in the list. So now we have bottom and top selected out for us. Now we can either draw a line between these two and measure the length of the line, or we can just take a distance component and measure the distance between the two. I'll throw a line in here just for the visual confirmation, but now you see we have this very nice line from top to bottom, so that's perfect. So now that we have this distance, we can see that it's 183. So now that we have the distance, we can compare this with the real height of a person and do a scaling factor that way. So I usually measure height in feet, being from America, but I always run Rhino and Grasshopper in millimeters. So if you ever want to convert values, we'll look at that too, just to be safe. So I'm going to go for an average height, 5.5 feet, and we'll use that millimeter value as 1600. And we'll come back to Grasshopper and plug that in. So this is the actual height of an average person that we'll want to get to. And right now we're measuring this person at 183. So we're quite a far ways off from true height. So this is pretty small right now, which is good to know. So we can use the scale component to scale up the person. So we'll have the geometry to start, which is what we want to scale up. So we can start by scaling the person. We'll get to scaling the jewelry in a second. We have the person. We want to know what the center of scaling should be. Right now, using 0, 0 is fine. We can move this point if we need to, but it's not going to be crucial for this workflow. And then we just have to find the scaling factor between the real height and the measured height. So let's plug these into a division component, and we can see that dividing the true height by the measured height, we see we need to scale up by 9.11 to get to real height. So we'll plug that into the factor, and now we're getting the true height of a person, which is great. So now this is real height. So anything that we print that is on this body is going to be true to scale. So we want to do that for the jewelry as well. So we can do another scale with the same inputs, or we can do a transform by using the transform data into the transformation. And we can take the earring, which will bring that in as a mesh as well. So that's the mesh. This is the earring. And we can scale this earring up with the exact same transformation data. So let's go back up to a real person, and we can see that the earring has come along with it. So now the earring is true to scale in real life along with the person. So to go to 3D printing, we can bake this out, and we can export this final mesh, and when we print it, it'll be the correct scale. So that's the very simple process for scaling up using a digital body, measuring that against the real height, and scaling up your creation to true scale. That's how I do it. Pretty simple. So that's it for this tutorial. thank you for tuning in. As always, this Grasshopper script, if you want to download it and use it yourself, is going to be on Patreon, so you can go grab it there. If you have any questions or feedback, drop those in the comments, or we can have a longer conversation over on Patreon. So go check that out again. That's all for today. Hopefully you enjoyed. Hopefully you learned something. If you did, there's a lot of other videos that you can learn a lot more on my channel. So great to see you, as always, and catch you next time in class. Bye.